Okay, let's continue our look at a couple of sort of side features of linear programming. And in fact, we're not technically doing linear programming when we look at these two topics. So in our last class, we went through sort of goal programming as a way to conduct analysis that wasn't being driven by sort of the true objective. Instead, we were sort of looking at a loss function or a distance function, and we in the reading from WILDE, W-I-L-D-E, you'll see that the Thrifty Food Plan by USDA is actually generated through something more like a goal program where both the cost and the nutrition information are built in as constraints, and then the goal is to minimize the deviation from sort of the predicted or typical consumption pattern. Okay, sorry, I had to do a little slide cleanup there. So yeah, we have talked about proportionality being the linearity assumption in effect. If you double something, you get double the effect, assuming you haven't hit a constraint in the interim. And so that's one we're not going to violate because we are not going to deal with risk problems. But these other two we are going to deviate from, really as ways of thinking about furthering analysis. So research questions may require that we violate a couple of classic linear programming assumptions. So the optimization assumption, really, that one of the variables of interest in the problem should be chosen to be either maximized or minimized. We dealt with that one in the previous class, talking about building this loss function or deviation function and sort of coming up with an average deviation or a total deviation that gives us a way of sort of measuring how far we are from targets. And the other one we're going to deal with is divisibility. So the choosing of any real number, or really assuming we have non-negativity, some number on the positive side of the reals. Okay, this is the same thing that I showed in class the other day. So if we did something that was like a McDonald's sandwich menu, and here's just a few, maybe 7 or 8, for 8 of the McDonald's sandwich menus, prices, nutrition content, and said, what does it cost me to eat? Hitting all of these nutrition targets or nutrition requirements, using only the McDonald's sandwich menu, you see it's $40 a day. And then, of course, the real kicker is that you are just meeting the vitamin A and vitamin C requirements, and everything else you are, for the most part, outside of fiber, more than double what you need. Okay, and in some cases, well beyond what you're looking for. So, this is a model that, one, gives you an index, I guess, of what it would cost to hit all the requirements just from the McDonald's sandwich menu, but no one, that probably isn't realistic. And so what we really want to do is think about how would you incorporate someone having to eat from the McDonald's sandwich menu into their full diet, right? Or how close could they get, or what's the efficient contribution that could be made from the McDonald's sandwich menu? And so to do that, we implemented these slack variables as percentage terms. Okay, so we recognize that 2,500 versus 8,300 here and 30 versus 430 here are not the same units. So subtraction to get the slack would be a misstatement of things. But we can put it in percentage terms, the percentage slack relative to the level, because percentage is a common feature. So all we would be doing here, if we added up all of the slack, would be asserting that all of the constraints are equally important. Okay, so we got rid of the units problem, but we do still have the everything here is equally critical to doing critical in terms of measuring deviation from the target. So this is just what I was saying. So it's not an implementable plan. It's pretty low information because the McDonald's sandwich menu is not a place you're ever going to find vitamin A and vitamin C. And so it must be the case that the choice to consume exclusively from the McDonald's sandwich menu would probably not be someone who is paying close attention to the vitamin A and vitamin C contributions. They may not be paying much attention to anything. And so we ran through this. We got rid of a calorie does not equal a gram of fiber and used those percentage results and ran this and saw that on $10, this would be the slack outcome you got. So, but the problem here was we had both positive slack and negative slack. So you either fall short of a constraint by 18% or you overshoot a constraint by some large amount. Okay, and so it's not a desirable result. It tells us to eat the full $10 and try to balance all this stuff out where we're over and under. And so, if we let this be sort of a two-sided problem where slack and surplus, right, the difference from the target, right, so a goal program is really about hitting a target. Well, we need to make it a target that is a target we either hit or fall short of, but we never exceed it, because then it says going over by the fat constraint by a certain percentage will help you out when you fall short on the fiber constraint by a certain percentage. So it's, in that sense, it's an art as much as a science. So if you read on through after the first 4 chapters of any linear programming book that sort of gets past the basic implementations, they start talking about the art of modeling and sort of being very intentional about what's included, about the implementation to hit the real research question, and not to be sort of ultimately constrained by what we would call the classical assumptions of linear programming. Excuse me. Okay, so we solved this problem, the diet problem, as a goal program, and the nutrition caps are in place, right? So you can go up, you can approach the target, but never exceed it. And we found that there were two different choices, the 2.4 hamburgers and 0.35 of that big tasty sandwich. The cost is $2.80. The total loss is $5.49, and the biggest slack you could get in this problem is 10 constraints times 100 percentage points, so 1,000. And so we are, the loss or the distance here is 55% of the total. So we're well away from finishing out a daily meal, but we also have a sort of a daily nutrition outcome, but we are much closer to what we might consider someone doing a partial, being required to sort of partially meet their nutrition needs by grabbing a sandwich or ordering quickly from the sandwich meal at McDonald's. You hit the targets for a couple things, so that means the rest of the day, if you do consume this, you will be only consuming excess fat and sodium. It's also an indication that these are sort of the most prolific things. We have hard caps in the model, and so it must be the case that fat and sodium are high supply items in the McDonald's sandwich menu, which isn't, any way a surprise, especially the subset of sandwiches I chose. I don't think there are many there that would be that. So what do we learn? What are the problems? Well, I guess the main approach would be to get away from something that is sort of funny and shows that, you're going to be spending a lot of money to subsist on 8 different sandwiches from McDonald's, but if it's not a true cost index, if it's not giving McDonald's sort of the fair chance to say, you come in, look at what we have, then how good of a cost index is it? And then we also learned that we might be able to think about someone who has a real world condition or problem. They are away from home. They order food for convenience, and so think of someone who's traveling and essentially can't carry their food with them or prepare food and bring it with them. If they have to consume once a day off of this sort of drive-through, this might be those 8 choices, or if you expanded it, might be a decent way of thinking about sort of in this sense, what does someone's nutrition look like if we had that, right? And so what we might learn is a way to, I'm supposed to open the spreadsheet. Let me pause and bring that up. Okay, I have this solution opened up in the spreadsheet here, so 2.4 hamburgers, 0.35 of the tasty sandwich. And so what we might learn is, okay, if we're going to construct a model and we're going to pick, looks like I have more sandwiches here than I intended, so I have 11. So they're all not copied over into that slide. But what we learn, or what we might do, is have this sort of process that's similar to what, if you read the original Stigler paper, where they go through and they select, and they say we have, I forgot what the number was, 100 foods or something total, but we in 1930 or 1940, whenever that was written, we don't have the computing power or the ability to solve that large model, and so what we're doing is sort of siphoning off things that aren't competitive. And so what we've done here is sort of think about, if this is the target, and let's just admit to the fact right away that we're not going to consume exclusively from these 11 foods, but what are the foods that we might be choosing, right? What are the sort of efficient choices? And so if you have sort of a restriction on the number of choices you want to put in, or if you want to think about building out somebody's choices for the day, someone's realistic diet, and incorporating the fact that they have to eat some part of it away from home, this might give you a good guideline to do that model in 2 parts. So we say that they get this quantity on sort of the constrained away from home part, and then what's left for them is to take all the choices on food at home. You could even think about it as sort of a breakfast composition and a dinner composition, and build that out. And so you would have a model that requires them to consume 2.4 hamburgers, 0.35 big and tasty, right? That would be hard constraints in your model. You just force those 2 things in, because you're saying, in this preliminary model here, I want to find the efficient choice. I know this person that I'm modeling has this sort of lifestyle constraint that says they have to eat away from home. Because if you put these in a competition with everything else and say, let's pick the foods for the day, and ignore their sort of traveling or constraint that they have to choose from this menu at some point during the day, well, you're going to get a much lower cost and a much sort of healthier diet, but you will have lost the fact that they actually have this sort of lifestyle constraint. So that's what we're trying to learn. We're trying to think about this sort of art of putting together a diet problem, and from that, thinking about how would we, if our ultimate goal was to sort of research what taxes on fats may look like or something like that, we have to build that in and not let them be starting the problem with something that isn't sort of their base case, right? So this would give us sort of that justification. I'm not recommending that you spend a lot of time thinking about goal programming, but I just wanted you to be aware that it could be this sort of informative way of looking at a sub-problem, okay, within sort of the classic diet problem here, because the classic diet problem we saw doesn't fit very well. Okay, so let's get back to the slideshow. And so that was our solution here. What do we learn? Well, we talked through it. There are additional problems, obviously, If you solve that problem as a sub-problem first, or as a sort of preliminary setup, and then go on and say, okay, I'm going to constrain the full daily model to get 2.4 McDonald's hamburgers and a third of this Big and Tasty. Well, if prices do change, or if you do incorporate something like a fat tax or a sodium, some labeling that tries to drive people away from sodium or makes them impute some cost from that, you have to, these consumptions, if they are built in as hard targets, as sort of fixed entries, then you're not allowing the model to respond to that. So we'd have to deal with that. It probably means going through both stages of the model again. Okay, so something like that, or building something, I guess, would be, since I'm talking about it, building something that requires a certain amount, right? We have a solution here that says about 45% of the slack is the potential slack is taken up from this model. We could probably build something that says, okay, you're going to have to get a couple of servings off this menu every day, and it's probably going to get to a certain amount of, we could probably choose those serving amounts based on sort of the contributions toward total slack. Okay, and so rather than making a hard decision on you must consume 2 hamburgers, you must consume part of one of these sandwiches, changing that around, saying, okay, well, you need to make a choice of this or this or this, and those have to be present in at least 1 serving or 2 servings from this McDonald's menu to sort of complete the realism of the diet. Additional problems, well, the big one is McDonald's won't sell me 2.4 hamburgers, so the cost here of $2.80 is not achievable because they're going to make me choose 2 or 3 for the hamburgers, and they're going to make me choose 0 or 1 for the Big and Tasty. And so, do I buy the 2 or 3, or do I buy Big and Tasty or not? Well, that is a problem that we could handle. It would not be consistent for us to if we're going to the trouble of modeling this, it would not be consistent for us to just round it off and say, well, that one rounds to 2, that one rounds to 0, because now all of our nutrition information is much shorter relative to the constraint targets, or to the nutrition targets, than we expected. But we could put in an integer constraint. So really that's the point of this second lecture, is if you put these into this second component here, is to if you put these integer constraints in, how do they work, and what are the sort of effects that you realize? So for those of you who, and I don't think anyone isn't aware, integer constraints just means any number can be written as something like a base x plus some fraction a over b. If a can be reduced down to 0 in some way, right? If you can get a to be 0 through some reduction or simplification, then what's left is an integer. So if 0 over b is the fractional part, then you have an integer. There's nothing after the decimal, some people might say. So for solver, an integer constraint can be implemented just by choosing int. Okay. So let's do the diet problem with goals and integer constraints. You can see I've already got it in bold here, so we know what the solution is going to be, but let me pause and bring up the spreadsheet. Okay, so we have our previous solution of 2.4 and 3.5, and so I'm going to go to solver and force this model to adhere to McDonald's rules, which say you buy the sandwich or you don't buy the sandwich. So we're going to add a constraint, and that cell reference is going to be right there for the hamburger, and we're going to say instead of choosing a inequality or an equality sign, we're just going to choose integer, int, and it just says that D5 must be an integer. We click OK, And then we add another constraint that says D12, the big and tasty, should also be an integer. It tells us that's good. Click OK, and then we click solve. Okay, so we hit a small gap here. One, a small hang up. We got the hamburgers down to an integer value, but it turns out the solution was to kick away the big and tasty, lower that to 0, and then now tell us to eat something like 2/3 of or 5/8 of a quarter pounder. Well, McDonald's has the same restrictions on buying a quarter pounder as they do everything else, so we really should have just chosen everything in this vector to be an integer constrained. I want to look at the solution picture here. And see that solver found a solution, constraints and optimality conditions are satisfied, but the only thing it gives me is an answer report. And so that's something we're going to watch and check on when we rerun this and fix it. So let's decline to save that solution, go to solver. I'm going to delete both of the integer constraints that are there and just add one that takes up the entire column. Okay, so everything on that column needs to be an integer, and we click solve, and it says solver found an integer solution within tolerance, all constraints are satisfied. It again only tells us there's an answer report, and it says there's probably a better solution, or there could be a better solution. There's not. This is a small problem, but it tells you that you can look in the options. But the real issue here is that we only get the answer report, and so we should ask ourselves about that. And it hopefully would make sense, because having an integer solution is quite different than having a corner point solution. When you're at the corner, you get things like how much can the problem adjust, and then where do I go for my next solution? Or you can simply say something like, if that constraint, the right hand side of that constraint expands out 2500 to 2501, well, you get a small movement in the line, a small movement in the corner, but changing that corner, right, by a small expansion of the right hand side does not change the nearest integer value, right? It doesn't, unless the corner originally wasn't an integer and now it is. So there's some sort of special cases where the math just lines up. But it must be the case then that we just don't have the ability to do sensitivity analysis, at least automatic dual type sensitivity analysis in these integer problems. If you add integer constraints, you lose that ability. So here's what the answer report looks like. It tells you which constraints might be binding, and then of course the integer constraints are forced, right? So they have to bind. You see here you're not getting, you didn't get any ability to do sensitivity analysis, so it wipes it away. And we'll look at the slideshow. We'll wrap this up. This is going to be kind of a short lecture to see why that would be. But the first thing to do is, if we had predicted, if we'd used the non-integer model, right, the one that took whatever and just rounded things off, we would have completely missed what solver is telling us is the best solution given a set of integer constraints, which is 1 cheeseburger, 1 fillet of fish. The total loss is 600, so instead of being 550, it's bigger, right? So this is a worse solution. We knew that had to be the case, because being forced to choose from integers is a reduction in the available choices, and the cost went up to $294. We're worse off because McDonald's will not sell us parts of hamburgers and Big and Tasties. That just makes sense. We're paying more for less nutrition, right? Because we're measuring nutrition now as the distance from our targets. So we have, some information here that says, rounding off the linear programming problem to approximate the integer solution it just won't work. Now, if it's small, if the if the fractions are small, you're probably okay. But to be sure, or to understand why that's not the approach, we can just look at a simple graphical problem here. So we have an objective equation represented by this dashed line, a feasible space represented by this, some four-sided figure here, quadrilateral, and it has this corner point, and so the payoff as you move out to the right hits this corner. And so, you can see, how do we get our normal sensitivity? Well, you would say if this constraint right here shifted out to the right a little bit, the payoff function would advance. It would, the slope stays the same, so the corner moves out, we get some small increase, and so increasing this right-hand side value attached to this boundary has some shadow value. Well, that's good, and that's fine, but the real issue here is now we added integer constraints, so the corner's not the solution. It has to be one of these nearby integers, and so if you think about it, this is still the objective equation, and in this case it's a maximization problem, so the objective equation is trying to push that level curve, that dashed line, this way. Well, you just start taking it back to find a new feasible option under the integer constraints, and I'm pretty sure this is the problem you hit first. The combination, the integer combination you hit first, 6 and 3. So the solution up here is something like 5.8 and 5.4, something like that. And to round that off, we might say let's go to 6 and 5, but you can see that if you round this up, right, this number is very close to 6 but not 6. If you round that up to 6, well, that's infeasible, right? And so that's why rounding is always a problem. Rounding in linear programs typically can only be done in one direction, so you'd have to pay attention to the constraints to maintain feasibility. But then the integer solutions, the integer combinations that are feasible, all lie within this feasible space, and so the true solution, the integer solution, comes from letting this objective equation push back and find the farthest from the origin, so to speak, feasible combination, and it would be down here. And so instead of getting something that's like 5.8, 5.4 and rounding it, or even rounding it down, the solution is actually to jump all the way down here to something that is 6 and 3. So it may not be nearby in the normal way we might think of space in the graph. It's really, given that this is the slope of the objective equation, what is closest to the boundary? What is nearest to its boundary? So it's probably the case that the boundary that is nearest in slope to the objective equation, and then what integer combination is going to be nearest to that would be sort of the spatial way of thinking about that. Okay, so yeah, the rounded solution here they show to be, this is from an old textbook, but I like the graph. So the nearest rounded solution is 5 and 6, and you can see that it is demonstrated here to be infeasible. The rounding rules that say round to the closest, so that's the true rounding solution is infeasible. The linear programming rounding rules would say round to the nearest feasible integer combination, and those are back here at 5, 5, but the objective equation is worse, right? If it moves interior, then it must be worse off. Then it must be the case that the optimal, and this is called integer linear programming, is what the IOP stands for, is right there. Okay, that's the end of that. So these are just a couple of quick tools or a couple of things to think about as you implement this. So if you do want to produce an integer solution or to force something in your model to be integer level, one, have a good reason for it because you are going to lose your sensitivity. There's just all the algorithms that incorporate integer constraints will take away your ability to do sensitivity analysis. So you might think about trying some other approach, putting in a minimum that forces something to its next integer level, a non-integer constraint. If you know it's costly to force something, well, it has to be still feasible, but if you know it's costly to force something to, for example, here, a way to get around this, if it was important to us to preserve the sensitivity, would to be not just round off the solution and not make it integer, but to force this not to exceed 5. Okay, and so part of the condition here that these are so different comes from the fact that this problem is 2 variables, right? So in 2 variables, you get this space, this feasible integer space of dots. But if you have more choices, many more choices, then you get many more dots, whatever the version of a dot is in multiple dimensions. So that may be the case. And then on the goal programming, I guess my sort of closing comment on that one is always, look, in your problems, in your solution, in your tackling of a problem in this class for your final, if you don't want to include all 10 constraints, right? If you're dealing with a problem, one option would be to just drop the vitamin A and vitamin B and calcium and iron, because if those are hard constraints for you to hit and you still want to think about the economics of these things, then that's fine. But you also might model these not as hard constraints but as a set of targets, and you want to get as close to them as you can, so you might incorporate that via some sort of a goal program or something. The other thing to do is you could add something like a supplement, sort of a low-cost supplement, and say, there are all kinds of choices and options to deal with if you find that you're really interested in sort of the fat, carb, protein sort of mix that drive calories, if that's really sort of the point you're interested in. And these 4 things here that not a lot of people sort of pay attention to, or a lot of people actually do supplement for them, then the simple thing to do is just find some off the on the market vitamin that contributes to all of these, and just say they're going to consume that and add the cost to it and drop it right out of your analysis. But the goal programming thing is kind of interesting. The typical use of it is competing objectives. Okay, so the idea that we want to eat at low cost, but also maybe conserve time spent preparing meals, right? So those are competing objectives. So you can either put one in as a constraint and set the other one as the objective, or you can come up with some sort of targets for cost spent and time spent, and come up with some sort of combo objective. So anyway, it's just it's a deviant deviated approach. I guess it's not deviant. A deviated approach that still deals with all the kind of constraints we're talking about, and of course it has a natural abridgment to estimation, because estimation is all about error or distance, and minimizing those to come up with a best fit parameter. In this case, would be coming up with the best fit plan, given some constraints. Okay, this is kind of short, but that's all right. I just wanted to kind of wrap these two things to put some things in your head, and mostly to help you with those readings, which I'm encouraging you to browse, go through as you try to develop your problem statement, and obviously keeping the models simple enough that it feels like you're doing a final exam is important. We're not trying to learn new techniques right at the final exam. What I really want you to do is really think about formulating a problem statement and a model that is a clear address to that problem statement and provides quantitative output that directly relates to the problem statement, and then also demonstrating your knowledge of sort of the quantitative linkages, right? So I got this result. It is a quantitative result. What is there in the data, in the nutrition information, that drove me to this result? Because that's the only way you're ever going to be able to think about sort of what are the limitations, what additional work or what additional sort of incorporation might make the model a better test or a more complete test, and then what are the expectations on the sort of final findings of something that is a much more research or more developed set of analyses. Okay, with that, I'm going to close this out, and I will either see you in the office or when we get back on December 3rd, when we will meet in our normal classroom, unless you hear differently. Thanks.